Have you ever stopped to think about how your body built your skeleton? I mean, it's an incredible engineering project that turns soft, flexible tissue into a strong, supportive frame. And this whole construction project starts way before we're even born.
So that's the big question, right? How on earth does this happen? How does a bunch of soft cells follow a precise blueprint to create over 200 bones, each one perfectly shaped for its job? When you think about it, it's a total marvel of biological engineering.
Well, there's a name for this whole process, of course. It's called bone ossification. This is the master plan for creating bone. And just like any master builder, the body doesn't just use one technique. Oh no, it actually has two very different methods in its toolkit, depending on exactly what kind of bone it needs to build.
All right, let's pop the hood and take a look at the actual blueprints. We're about to see the two fundamentally different but equally crucial architectural plans our body uses to get the job done. Okay, so here they are, side by side. On one hand, you've got intramembranous ossification. Think of this as the direct build method. It's used for flat bones, like your skull, where bone forms directly from a sheet of soft tissue. And then there's endochondral ossification. This is more of a scaffold and replace job. The body first builds a perfect little model out of cartilage and then, piece by piece, replaces that model with real bone. This is how most of our skeleton, like our arms and legs, is formed. So let's dive into that direct build method first. This is a specialized process, a kind of express route for making bone, and it's used for some of the most critical flat bones in our body, especially the ones protecting our brain.
And here's why this method is so brilliant. At birth, a baby's skull bones aren't completely fused together. You know those famous soft spots? They're there by design. This flexibility allows the baby's head to safely compress and pass through the birth canal. It's just a perfect example of function dictating form.
So how does this direct build actually work? Well, you can think of it in 4 steps. First, site prep, a bunch of stem cells cluster together, basically marking the construction zone. Then, the real builders, cells called osteoblasts, show up and start laying down a soft, unmineralized foundation called osteoid. Step 3 is hardening. Calcium is brought in, which mineralizes the whole thing and traps the builder cells inside. These trapped cells then mature and become osteocytes. And finally, the finishing touches. The whole structure organizes itself into spongy bone on the inside with a hard, compact shell on the outside. Quick, direct, and incredibly effective. All right, now for that second blueprint. This is how we build our long bones, and it's the body's most common method. And it starts not with bone, but with a really clever temporary stand-in. This quote right here really says it all. The body doesn't build the final product right away. First, it creates a perfect miniature model of the bone out of something called hyaline cartilage. Then, and only then, does it begin the process of replacing that model bit by bit with actual bone. The process kicks off with that perfect cartilage blueprint. Then, a hard bone collar forms right around the middle, which cuts off nutrients to the cartilage inside, causing it to break down. This creates a cavity, and boom, blood vessels move in, bringing our bone-building osteoblasts with them. This becomes the primary ossification center. Later on, after birth, the exact same thing starts happening at the ends of the bone, creating secondary ossification centers. Now, this whole scaffold and replace method has a secret weapon, a really cool feature. It doesn't just create a bone, it creates a bone that can get longer. This is the engine of how we grow taller all through childhood and our teenage years. And the key to all this growth is the epiphyseal plate, which you've probably heard of as the growth plate. It's a thin slice of that original cartilage model, kind of sandwiched between the middle of the bone and the ends. You can picture it as this busy, on-site factory constantly churning out new cartilage on one side while bone replaces it on the other. It's literally pushing the ends of the bone further and further apart. Okay, if we zoom into that factory, we can see it's basically a production line with different zones. It's fascinating. So a cartilage cell starts in the proliferative zone, where cells are just dividing like crazy. As it gets pushed down the line, it enters the hypertrophic zone and it swells up, getting bigger. Then in the calcification zone, the area around it hardens, the cell dies, and it leaves behind a perfectly shaped little space. Finally, in the ossification zone, our builder cells, the osteoblasts, move in to fill that empty space with brand new, hard bone. That incredible assembly line is what makes us grow. But of course, all factories eventually close down. Sometime in early adulthood, hormonal signals tell the growth plate to stop making new cartilage. The production line grinds to a halt, the little bit of cartilage that's left turns to bone, and that's it.
Lengthwise growth is complete. You've reached your final adult height.
So you might be thinking, this biology is cool, but why does it matter to me? Well, because these growth plates aren't just part of our history. They are a living record of our development that doctors can read like a book.
You know, when a doctor takes an X-ray of a child's hand or knee, that active growth plate shows up as a dark line or a gap. That's not a fracture. It's because the cartilage is way less dense than the mineralized bone all around it, so the X-rays just pass right through.
And by looking at the size and shape of these gaps, doctors can figure out a child's bone age and see if their skeleton is developing on track. But these gaps also show a vulnerability. The growth plate is the weakest part of a growing bone, so a fracture there needs immediate and really careful attention to make sure the bone keeps growing correctly and doesn't end up shorter than the one on the other side.
So when you think about how our skeleton is built, it all comes down to this number, 2. 2 incredible and totally distinct construction methods. You have the direct build for our flat, protective bones, and that clever scaffold and replace method for all of our long, growing bones.
And that brings us to a final thought. We've seen this epic construction project that basically finishes up in our early 20s. But the work is never truly done. If the building stops, why is everyone still so focused on bone health, on density and strength later in life? Well, that is a great question for another explainer.